Okay, so just to remind you as a review of where we were last time, we were talking about the translation operator. And the translation operator we're writing as T of A. It depends on a parameter A that's telling you how much you're translating by. And it's given by the exponential of minus I times A times the momentum operator divided by H bar. And this turned out to be unitary. Okay, and so we can summarize what it does either in the active view, which is a way of saying what it does to states. So acting on states, TA acting on psi, or sorry, let's not do it for psi, let's do it for x first. So acting on a state where the function is known to, the particle is known to be at a position x, gives you back a state in which the particle is known to be at x plus a. And so as a consequence of that, we worked out that this matrix element, x ta for any state psi, is equal to the wave function, but evaluated at x minus a. In other words, the state Ta acting on psi has the same wave function as does the original state that we were acting on, but with x replaced by x minus a. Okay, so that's the active view. And then there's alternatively the passive view, which is what we actually did first last time. So the passive view is how operators transform. Okay, and that says TA dagger x TA, that operator combination is just x plus a. Okay, so this is the passive view, this is the active view. And I want to emphasize both of those equations are equally valid and they're always true. But it's just that they summarize in different ways how translations work. Okay, more generally than just talking about position eigenstates, you can say what it does to any state. So TA acting on any state in words is just, I'll put this in brackets to mean this is a verbal description, is the state psi moved to the right by a. Okay, and TA dagger on any operator, omega, TA, is equal to, the verbal description is it's the operator omega with the coordinate system moved to the left by a. Okay, so for example, so the previous boxed equation is just what happens when omega equals x, but you could ask, for example, what happens if omega equals the momentum operator. So for example, TA dagger P TA is just equal to P itself, which makes sense because TA is made out of an exponential of P. P always commutes with itself, so it just moves past, they just move past each other. So this is the passive view of what happens to a momentum operator. Okay, whereas on the momentum eigenstates, if I look at TA acting on a momentum eigenstate P, Now I can just take the p that's within the exponential and replace it by the number p. And so this is the exponential of minus IA. I'll write it operator first, but now the operator turns into a number. Okay, and that number is in fact just a phase. So it's not affecting what the state is really. And so this is the active view of how things work in a momentum eigenbasis. Okay, so now suppose we take any state and we act on it with the translation operator, and let's ask about expectation values. So if we take any state psi and replace it by translation operator acting on psi, okay, then, for example, the expectation value of x is going to transform in the following way. It's psi ta dagger x ta. Notice you can either do this in the passive view, where you think about x as transforming, or you can do it in the active view, where you think about it as the psi transforming, but either way, it's the same thing. And then that's equal to psi x plus a psi. Okay, and the number a we can just pull out. And so this is equal to the expectation value of psi, expectation value of x in the state psi plus the number a. There I'm assuming the state has been normalized. Okay, and so what has happened is if you do a translation, just as you might expect, the expectation value of x gets replaced by itself plus a, and the expectation value of the momentum, if you shift everything by a, doesn't change. Okay, so expectation values behave in sort of the expected way. Now let's think about the special case of an infinitesimal translation. So that just means we're going to take our parameter a and we're going to replace it by an infinitesimal number epsilon. T of epsilon is 1 minus I epsilon over h bar times the momentum operator. We can just throw out anything higher order in epsilon. And so the way we describe this in words is by saying that momentum is the generator of translations. Okay. Now suppose that the Hamiltonian is invariant under translations. That's a very special situation, but it can happen. Suppose that H is invariant under translations. So an example of that is if the Hamiltonian is a free particle Hamiltonian, then that will be true. And if it's the free particle Hamiltonian plus any function of just momentum, okay, then all those momentums just commute with the exponential. And so this would be an example where, yes, it's true. But for example, the problem that we will start doing in depth after the midterm, where the Hamiltonian is p squared over 2m plus 1/2 m omega squared x squared. That's the harmonic oscillator Hamiltonian. That would not fit this description. It's not invariant under translations. Okay, but we're supposing it is. Okay, and then that means that for an infinitesimal translation in particular, T epsilon dagger H T epsilon in the passive view should just be the Hamiltonian back again. And so if we write out what that means 1 plus I epsilon over H bar P. That's T epsilon dagger. The I flips sign, but P is Hermitian, so that's left alone. Times H times 1 minus I over epsilon over H bar P. That should be equal to H. Excuse me. Okay, and if we rewrite that, that says the Hamiltonian plus I epsilon over H bar, commutator of P with H, plus, there will be an order epsilon squared term, but this is infinitesimal, so we're going to neglect that. That has to equal on the right-hand side H. The H's cancel. And so if the Hamiltonian is invariant under translations, that's the same thing as saying that the momentum commutes with the Hamiltonian. Okay, so this has consequences. One is, if you're invariant under translations, there is an orthonormal basis of common eigenstates. Of the Hamiltonian and the momentum. So of common eigenstates of energy and momentum. Another consequence is that an eigenstate of momentum will remain so at later times. So we can prove that in one line as follows, that if we take the momentum operator acting on the time evolved state, remember we learned how to do time evolution with this unitary operator e to the minus I Hamiltonian T over H bar. If we do that acting on a momentum eigenstate and P commutes with H, then we can just move the P here right through the exponential and have it turn into P the number when it gets to here. And so this is, and then bring it out again. So this is P times e to the minus I HT over H bar acting on P, which is saying that the whole state here was indeed an eigenstate of momentum. Okay, and then the third thing, the third consequence is that an expectation value of momentum for a more general state, not necessarily an eigenstate, is going to be conserved, meaning it's not going to change at all. So this is in any state. Okay, and this is actually a consequence of something more general that we're going to talk about now. So this is a consequence of what's called Ehrenfest's theorem. Okay, so this is going to be a little aside for Ehrenfest's theorem. So Ehrenfest's theorem is not just concerned with momentum operators, but with any operator, and it talks about what happens to the time evolution of any operator. So let's consider of the expectation value of any operator. So let's consider the time derivative of the expectation value of an operator A. an observable A, okay, which is defined to be the time derivative of the matrix element psi A psi. Okay, and this is for an observable A and some state psi, where the expectation value is to be defined. Okay, so to think about this thing, what we're going to do is just take the derivative, and the derivative splits into three parts because the state psi could depend on time, but the operator A could also. So the three parts are going to be d by dt acting on the bra psi on the left by the product rule, plus the bra psi A times the time derivative of the ket psi. And then there's the third piece is psi times the time derivative of the operator itself. Okay, now the partial derivative here on the A is meant to indicate that this corresponds to the dependence of the operator on time, which is very often 0. In fact, it's equal to 0 for example, our observable A equals x, or for our observable A equals momentum. And you could say, well, in classical mechanics, position and momentum change all the time, but that's not what we mean by dependence of the operator. But by dependence of the operator, we mean really the explicit dependence. So if it had some time built into it, into the definition of the operator itself, then it would depend on time. But just because the classical version changes with time would not make this object change in time. Okay, and so very often that's 0, but we'll keep it around just in case A has an explicit time dependence. And then, for example, this part, we know from the Schrodinger equation is minus I over h bar, Hamiltonian acting on psi. And this thing right here is just the Hermitian conjugate of that. So this is plus I over h bar psi h. And so now we can rewrite everything by noticing that we have h acting on A minus A acting on h. So this whole thing is minus I over h bar psi commutator A with h psi. Okay, plus psi partial derivative A with respect to psi. And now it's reassembled back into a sum of expectation values. So we can write this as the time derivative of the expectation value of A is minus I over h bar, the expectation value of the commutator of A with the Hamiltonian, plus the expectation value of any explicit dependence of the observable on time. So this is often 0, but not always. Okay, and so that equation is Ehrenfest's theorem. All right, so this has more applications than just the one that we are dealing with immediately. The one that we're dealing with immediately was that if the system is invariant under translations, then A is the momentum operator. Okay, and we go back up to here. And that tells us that this term is going to be 0. This term will also be 0 because the momentum doesn't explicitly depend on time. And so all of this is telling us that in this special case, the time derivative of the expectation value of the momentum operator in any state is equal to 0 if the Hamiltonian commutes with the momentum, which is true if the Hamiltonian is invariant under translations. All three of those statements are equivalent. Okay, questions on that? All right, so let's bump it up a notch and just do things a little bit more generally than what we've just done. Instead of considering translations as special, let's consider a general continuous symmetry. And basically, everything I've said about translations is going to work out exactly the same way for a general continuous symmetry. Okay, and so we suppose that we have some operator that I'm going to call G for generator, and it's Hermitian. Oops. Okay, so this is going to be the generator of the symmetry. In the previous discussion, it was the momentum. And so what we're going to do is define a unitary operator built out of it. First, we're going to do the infinitesimal case. So we're sort of doing everything in the reverse order from what we did for momentum. So this is defined to be the identity operator minus I epsilon times the generator divided by h bar. Okay, and now we're going to let epsilon be some parameter a divided by a number n, which you can think of as a large integer. And we're going to repeat acting with this operator n times. Okay, now recall, probably you may not remember this from the first time you learned about the exponentiation operator, but the way the number e is defined is if you take the limit as n goes to infinity of 1 plus x over n to the nth power, that's equal to e to the x. Okay, that's the sort of basic definition of the exponential. And so now for an operator that's built out of only one other operator, so it commutes with itself, we can just apply that to this situation. And so the unitary operator for a non-infinitesimal number, can be defined as the limit as n goes to infinity of 1, I guess I should technically call this the identity operator, minus I a g over h bar divided by n to the nth power is equal to the exponentiation of minus I a g over h bar. Okay, and this is a unitary operator, as suggested by the fact that we gave it the name u. Okay, so now built out of that unitary operator, we can talk about symmetry transformations. Either in the active view or the passive view. So if I have any state, psi, and I act on it with u of a, I'm going to get a state that I can call psi sub a. So this is equal to u of a acting on the original state psi. So this is in the active view. The notation psi sub a means it's the state psi transformed by a. In the translation case, that just means we translated the state by a. But more generally, it could be some other symmetry operation. Okay, that's the active view. And then the passive view is if we have an operator omega, we can transform it by A by doing U A dagger omega U of A. Okay, and so again, this is the transformed operator. Okay, now there's a special role to play if the Hamiltonian is unchanged by this operation, whatever it is. So if the Hamiltonian is unchanged, then UA dagger Hamiltonian U of A is supposed to equal the Hamiltonian. And then by exactly the same steps that we did before, that means the generator commutes with the Hamiltonian. So that commutator is 0. And then the consequences by exactly the same set of steps that we just did for translations are, 1, there is a basis of common eigenstates of the Hamiltonian and the generator. Okay, and 2, if you happen to be in one of those eigenstates of G, so an eigenstate of G, it's going to remain so at later times. Okay, and the proof is just the same as what we did before. And the third thing is from Ehrenfest theorem, the time derivative of the expectation value of G is 0. So that means even if you're not in an eigenstate of G, your expectation value won't change. Okay, and so a lot of times that's a very important thing to look for, is what are the symmetries of your system, the things that, the generators that commute with a Hamiltonian. Questions on that? Okay. Okay, so not all symmetries, though, are continuous ones. And the best example of one that's not a continuous symmetry is parity. And since we've already sort of seen some of the consequences of parity, parity, by the way, is also known as space inversion. Okay, and what is space inversion? Excuse me. It's what happens when you take x, the coordinate, and replace it by minus itself, and do the same thing for momentum. Okay, and so this is not continuous. You can't do an infinitesimal version of parity. There's no such thing. You either do parity, you either flip x to minus x, or you don't. Those are your two choices. There's no continuous infinitesimal version. Okay, so nevertheless, we can still make some similar statements to what we did for the continuous case. So first, let's define how parity works in a basis, in a complete ortho basis. So define in complete ortho basis, and we'll choose the position eigenbasis, x. Okay, and so the definition of the parity operator is acting on any state x. It gives back the state minus x. Okay, so first of all, because these are linear operators acting on a complete ortho basis, that means if I know how it acts on any element of the ortho basis, then I know how it acts on anything. because any state is some linear combination of the x states. Okay, and then the other thing I want to caution you is to be careful, because this state minus x is not the same as minus the state x. They're completely different things. Okay, this state minus x is where the particle is known to be at the position minus x, whereas this state, the particle is known to be at x, not minus x. The minus sign is just some phase multiplying it. And so these things are just completely different. Okay, so that's how we can define the operator. We could also, we can think of it as being defined by this, but it's nicer to have a statement like this one that's just true for every basis element. So now, for example, we can do the following. Let's say we act with it twice. So we take parity times parity, acting on the state x. The first parity operator changes x to minus x, and the second one changes it back to x. So this is just equal to x. And so that tells us, since that's true for any state x, that tells us that the inverse operation of parity is the same thing as parity. Parity times parity is 1. And so it's its own inverse. Okay, another thing we can learn is, let's say we take the Hermitian adjoint of this equation. And so that says x pi dagger has to equal minus x, the bra. And so if we compute the following matrix element, x prime pi dagger x, that's equal to minus x prime x from the previous line, which is equal to, we know how the inner products of position eigenstates work. So this is actually the delta function of x minus x prime, or x plus x prime. Okay, notice it's not minus delta x minus x prime. This is equal to, in turn, we can rewrite this as x prime minus x. And that we can rewrite as x prime parity operator acting on x, just from the original definition. Okay, and so what we've done is, for arbitrary x and x prime, we've computed the matrix element of pi dagger and pi and found out that they're always the same. So since this is true for every x prime and x, it must be true that pi dagger is equal to pi. Okay, and so the parity operator is both Hermitian and unitary. Okay, it's Hermitian because of this equation, but then this equation says that pi dagger, since it's equal to pi, is also its own inverse, so it's also unitary. And so what that means is it's got a rare double roll. It's an observable because it's Hermitian. And it's also something that maps a basis to a basis. That's what unitary operators do. Okay, and furthermore, we can figure out what it does to wave functions if we define the wave function, as we usually do, as the inner product of the x eigenstate with the state we're in, the state ket psi. then the matrix element X parity psi is equal to, we learned above, minus X psi. And so that's the wave function psi of minus X. Okay, so this is the wave function for pi acting on psi. Okay. Questions on that? No? Okay. So we should also figure out what the eigenvalues of parity are, because it's an observable. That means it's something we can measure. And so we should know what its possible measurement results are. So parity eigenvalues. Okay, and so we're going to solve the eigenvalue problem by looking for an eigenstate, let's call it lambda. Lambda is a label that's telling us what the eigenvalue is, so that pi acting on lambda is the number lambda times the state lambda. And now we act with pi again. Pi squared acting on lambda just gives us another lambda. Okay, but pi squared we know is the unit operator. And so this is just lambda, or the identity operator. So this is just lambda back again. And so that's telling us that lambda squared is equal to 1. Now notice that it's lambda squared. It's not the magnitude of lambda squared. And so there are two solutions. Namely, lambda can be plus 1. And that would tell us, from what we just found about the wave functions, that psi of x is equal to psi of minus x, which means it's an even wave function. Even under x goes to minus x. And the other solution is lambda is minus 1, which would tell us that psi of x is equal to negative psi of negative x. And so it's an odd wave function. So we encountered both of those when we talked about the particle in a box and the particle in a square well. And that's no accident, because in that, as we'll see, the Hamiltonian for that commutes with parity. And so they have common eigenstates. As further examples, though, of how we can act with parity to compute matrix elements. So let's say we consider the matrix element of a position eigenstate x with the parity operator with p. Okay, so that's equal to minus x times p. Okay, and we know what that is. That's e to the minus I px over h bar divided by square root of 2 pi h bar, which is also equal to x minus p. Okay, and so what we've learned from that is that the parity operator acting on a momentum eigenstate gives you back the eigenstate of momentum with the opposite momentum, minus p. Okay, so that means that the momentum eigenstate is not an eigenstate of parity. If it was, it would have given us back a number times p, which is not the same thing as minus p. Okay, so momentum eigenstates are not eigenstates of parity. Okay, also an example of what we can do is we can look at how operators transform under parity. So for example, suppose we take pi x pi. Okay, so if we do that acting on any position eigenstate x, we can compute that because we know how pi acts on x. So this is equal to pi times x times minus x. That's just using the first pi with its definition. And now x acting on minus x is minus the number x. And now we can act with pi again. That changes the ket minus x back into x. So this is minus x times the ket x, which is also known as minus the operator x acting on x. Okay, and that's supposed to be true for any ket little x. And so what we can conclude is that the operator pi x pi is equal to minus the operator x. Okay, and if you do exactly the same thing, but for the operator p instead, you get the same result. Pi p pi. By the way, that's why pi is the symbol for parity and not p, because we need p for momentum. This is equal to minus the operator p. Okay, so that's true for x and p, and we describe this by saying in words that the operators x and p are odd under parity. Okay, but not all operators, of course, are going to be odd under parity. Some of them will be even, and then some won't have well-defined parity at all. So more generally, if parity operator parity is the same operator back with a plus sign, then it's said to be parity even. Okay, and if, as the two examples we just did, if it gives back minus the operator, then A is parity odd. And then there are many examples where it's something else, neither of those two. So it doesn't have to be parity even or odd, then A is neither. Okay. So for the even case, there's something very special we can say that you can't say for the odd case or the neither case. If A is even under parity, then we can just rewrite what that means. That means parity times A minus A times parity is 0. So the commutator of parity with A is 0. And so they are compatible operators. Compatible. And so that means they have common eigenstates. Okay, and that was true of the square well, and it's also true of the free particle. Okay, so note, for example, for the free particle, parity times p squared over 2m, that's the Hamiltonian, times parity again, is 1 over 2m parity p parity, parity p parity. I put in two parities there, but that's just one. Okay, and then parity p parity is minus p, and this one's also minus p. But the minus signs cancel, so I get back p squared over 2m, which is even. So the free particle Hamiltonian is even under parity. Whereas if I have, let's say, something in the potential that's like x to the nth power, that will be minus 1 to the n times x. So if I only have terms in my Hamiltonian that have n equals even powers of x, then it will be parity even. So the Hamiltonian is even if the potential v of x has only even powers. Okay, so I think next time we will talk more about the consequences of parity. But I did want to say something about the last homework, because there was one problem that caused a lot of confusion. In fact, I think nobody actually got it right. So this is a comment on homework 4, problem 1F. And so there were a variety of things that people got confused about. One of them didn't actually have that much to do with the problem, but I wanted to mention it because it's an important conceptual issue that I think people are having. So people wrote down, a few people wrote down some version of the following equation. The Hamiltonian acting on psi of x is equal to minus h bar squared over 2m, two x derivatives acting on psi of x. Okay, so I want to emphasize that this is just not a right equation. Okay, and the reason is because it doesn't actually even make sense. The differential operators, for example, the second derivative, this is something that acts on wave functions, not on kets. Okay, and kets are not wave functions. They're conceptually different things. Okay, so if I write a ket, and so normally I wouldn't want to write it this way, but let's say I wrote it like that. The meaning of this expression can only be that this is the state whose wave function is the function psi of x. But that doesn't mean it is equal to the wave function psi of x. The wave function psi of x is the thing that has an x derivative, x dependence. And so you can talk about taking derivatives of it. It's equal to the inner product of x with psi. Whereas this expression on the left is not a function of x, despite appearances. The psi of x is just a label telling you which state it is. So that's why it's better usually, unless you really need to say that it's the state whose wave function is psi of x, it's better to just call this psi. Okay, so as opposed to this wrong equation that one should never write, what's the correct thing that one should write? Okay, it's that the Hamiltonian acting on the ket psi corresponds to minus h bar squared over 2m second derivative acting on the wave function. Okay, this is the corresponding wave function, but it's not equal. A wave function and a ket can never be equal to each other because they're just different types of objects. Okay, or Another correct way to write it would be this: x h psi. That means the wave function with respect to x of h times psi is equal to minus h bar squared over 2m, second derivative, x psi, okay, which is minus h bar squared over 2m times the second derivative of the wave function. Okay, so this would also be correct, a correct way of writing it. That it's sort of making what might look like an artificial distinction, but this this type of thing will get you into trouble in other situations besides this one. Okay, so be careful with the distinction between a ket and a wave function. But then the more immediate problem, or the more immediate difficulty for this problem, is that in this problem, the eigenvalue equation for the Hamiltonian looks like this. Notice I'm writing it in terms of the wave function because that's how the differential operator works. That is question mark equal to E times psi. And most people said, computed this and said, yeah, it works, but it actually doesn't. Okay, so this does not work. And the thing that goes wrong is, you can see this graphically if you just look at how the wave function behaves. There's the point L, and the wave function has this form. It's a cosine, and then it gets here, and then it just becomes 0. Okay, and so this second derivative is not defined. In fact, it's infinite at the point x equals plus or minus L. Okay, and remember, as the problem stated, this was a free particle, so it's defined everywhere. In fact, the statement of the problem was careful to mention that this is supposed to work for all x, minus infinity to infinity. Okay, so right here, there is a big problem. The second derivative is infinity, which is not equal to E. Okay, and so this is not an eigenstate of the Hamiltonian. Notice this is completely different from the particle in a box. Because in the particle in a box, you don't look at the point x equals L, because the particle's not allowed to be there. So I'll just say at the edge of the box. Okay, so in that case, there's no problem, and it really is an eigenstate of the Hamiltonian. But here, it's definitely not. Okay, so I just wanted to mention that. And let me ask if there are any other questions.
Sorry, Professor?
Yeah.
Has the room of the exam been determined yet?
Yeah, it has. So I just received an email during class, which said that the room is confirmed from 10 o'clock till noon on October 5th, and it's going to be in 121 Davis. So,
Where is that?
so next time I'll put out a more formal announcement of about the midterm.
Is that, I'm sorry, is that far from the home center?
It's right next door to the physics building. It's the next building over.
Okay.
So it's actually between the Holmes Student Center and the physics building.
Okay.
Okay. All right. So let me, yeah, I'll mention more about that next time. Let me turn off the recording here.